Now, drawing an alpha diagram is a real pain because it's a big and bulky thing and it takes a long time. So scientists, chemists and physicists generally try and come up with some sort of a shorthand. And the interesting part about every element is really the fact that the outer electrons are important in bonding. So what a Lewis dot diagram does is it takes dots and crosses and it represents the electrons only in the outer energy level. So by that we can say that group 1 has always only got one electron in the outer energy level. Group 2, 2. Group 3, 3. Group 4, 4. 5, 5, 6, 6, 7, 7, and 8, 8, or in the case of helium 2. As you can tell, this is not terribly complicated. So chlorine is in group 7, so here we have chlorine, and that means that it has 7 outer electrons. Yes, there's 10 electrons in the inner department, but that does not mean that we are going to draw all of them. We are only going to draw the valence 7 electrons, the outer electrons. So what I do is I go chlorine, Cl, not a great L, anyway, that's supposed to be Cl. And then I can either use dots or crosses to say the first two would be paired. Why? Because they would be in the s orbital. Then we would have unpaired, unpaired, unpaired. If I was drawing an alpha diagram, it would be 3s, 1, 2, 3p, 1, 2, 3. 4, 5, 4, 5. That is a Lewis dot diagram for chlorine. If I'm looking at magnesium, magnesium is in group 2, and so I am going to say Mg. And if magnesium is in group 2, it is going to land up. Again, we're in the third energy level, so it will be 3s, 1, 2. There will be 2 paired electrons. Doesn't matter if I use dots or crosses, I can use dots or crosses, and there would be 2 paired electrons. Electrons that are paired in alpha diagrams must be paired in Lewis dot diagrams too. So if we look at oxygen, first we can look at oxygen, draw an alpha diagram in our heads, and it's going to be 2s, 1, 2, 2p. If you want, you can put the 1s electrons in as well, but we're only interested in the outer electrons. 1, 2, 3, 4. So if I'm drawing oxygen, it's O, 1, 2 paired. Doesn't matter where I put those two, but I must show that they're paired. 3, 4, 5, and then 6. And again, that sixth one could have gone anywhere. What you kind of need to think of is if there's a little box for a pair there, box for a pair there, box for a pair there, and a box for a pair over there. Those are called Lewis dot diagrams. Sometimes we want to make it even more shorthand. Let's just take a look at phosphorus's alpha diagram. There's phosphorus over there. It is in group 5 and it is in period 3. So we are going to say, and altogether it's got 15 electrons. 1s, 2s, 2p. We get that from the periodic table. It's easy. First period has only got 2. Second period has got an s and a p. Third period an s and a p. Fourth one, we're only interested in the S. But you don't have to write all of those. We only need to go up to where we need to go to. So, phosphorus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Notice again, unpaired until I have got more electrons in the p orbital. So what am I going to do? I am going to go 1s, in the 1s I've got 2 electrons, superscript 2. 2s, in the 2s orbital I have got 2 electrons. 2p, in the 2p orbital I have 6 electrons. 3s, I have 2. Notice I'm using superscripts. 3p, I have got 6, at least 3. So that is what is called an electron configuration for a phosphorus atom. So if we were to just get given this electron configuration here, what can we see? We can see that my last electrons are in the third period, so we can see it's in period 3. And we can also see that in the third period I have got 2 plus 3, so that's 5 altogether. 5 electrons, which means that phosphorus is in group number 5, which makes perfect sense. So it's in period 3 and group 5. What I'd like you to do is to try and go through these questions over here, and you need to work through them while you've pressed pause, and when you unpause, then you can take a look at the answers. So if we take a look at these, you can see lithium's in group 1, 1 valence electron. Neon's in group 8, 8 valence electrons. Carbon is in group 4, 4 valence electrons, 2 paired, 2 unpaired. Magnesium is in group 2, 2 paired electrons. Notice that for the electron configuration, I have to write all the way from 1s. I don't just show the outer ones. 1s2, 2s1. And notice that in neon, I've got 8 electrons in the outer energy level, 4 electrons in the outer energy level, and only 2 electrons in the outer energy level. Now comes a slightly more interesting part. What about Na+? These are diagrams of the electrons. Now normally sodium would have 11 electrons, and one of them would be in the 1s orbital, in the 3s orbital. But the fact of the matter is this sodium has lost 1 electron, so it's going to look exactly like neon in terms of its electron structure, and you need to show that there's nothing there. Silicon, just an atom, no difficulty in drawing a Lewis dot over there. Notice you've got 2 electrons in the outer p orbital, and when you've got to draw fluorine, or rather the fluoride ion, this fluorine, instead of having 9 electrons, has gained 1 electron, so you need to represent 10 electrons. What's interesting to notice is Na+ looks exactly like F-, would look exactly like neon as well. So these electron configurations are exactly the same. By the way, oxide, when it becomes O2-, would also look the same. Beryllium ion, if it lost the 2 electrons, magnesium ion, if it lost the 2 electrons, would also look exactly the same, because if it were to lose its 2 electrons, it would look just like neon again. Taking a look at aluminium, aluminium is 3+ here. Normally aluminium would have 13 electrons, but it's lost 3 of them, so again it's going to have the electron structure of neon. Same is true of oxide. Oxygen normally has 8, it's gained 2 electrons, so it's going to look exactly like neon as well. Boron over here is the 5th element, so it's 1s2, 2s2, 2p1. They then ask you to differentiate between an atom and an ion. An atom is going to be a neutral element, whilst an ion is an element or an atom that has gained or lost electrons.